Greetings, everybody, and welcome to Tuesday's class video. I'm going to do a recap of what we talked about on Thursday last week, and we'll go into a little bit more energy and power today, and we'll see how far we go. As a quick update, homework 3 is posted. I've put as a due date the 28th, which is 1 week from today is Tuesday, so 1 week from today, or perhaps if you're seeing this a bit later, it will be the upcoming Tuesday. There will be quiz 3 enabled the same day, and usual deal, uploading of the homework and 1 full day to do the quiz. Pick your time, take your 45 minutes time and submit a quiz, and we will go from there. What I should probably also talk about is when the first exam is. And so we'll say, let's see, we're here on today's the 21st. So this is week 4, so week 5, week 6. So I'll say it's going to be in week 6. We're going to look at March 9th for the first celebration. That is the celebration of knowledge, because the word exam is, and it's not a midterm because it's not midterms, but celebration of knowledge I feel is quite reasonable. It has a fun connotation to it, right? So we'll be looking for March 9th on that. And a couple more reminders will be coming your way in the meantime. So let's do this. I'm going to do the virtual whiteboard for you today, since I am at home. So we are going to do the best we can here. I don't have any demos to show this time around, but we'll talk about a few things, which hopefully then I can go back on Thursday and I'll grab some stuff out of the stock room, and maybe I'll be able to show you a few live things. In terms of energy and power, energy we talked about is the ability to do damage. And I came up with a couple of ways that could happen. One being that an object was moving, right? So due to the motion of the object, say, for example, you put a piece of glass in front of it, it smashes into the glass shatters. That's your ability to do damage. So through motion of an object, and ultimately through anything else that causes motion. And one of them I alluded to was the height, because if I drop something from higher, by the time it gets from all the way up here to all the way down here, it's moving faster, and therefore it must have had something that it transferred into the motion. All right, so we might say height, and that would be height above, well, for us, height above Earth. That would be if you lived on the moon. That would be the height above the ground. Maybe more in general would be a better way to think about it. We have also the law that tells us that these two ways to have energy can transfer between each other. All right, so we can say, well, I can take the motion, and I can take the height. I can take whatever energy I get from motion, and I can take whatever energy I get from height, and I can say that they transfer between each other. They have the ability to transfer. And this is an offshoot of our law, but it illustrates it reasonably well. Certainly, it doesn't prove it. Remember, we can't prove anything in science, except that if something's wrong, we can do that. We can't prove anything correct. This here is an outcome of our law of energy conservation. The idea that energy starts as maybe one form, or I likened it to pouring water from, pouring water from bucket to bucket, or having water that I'm going to divide up into buckets, or I have a bucket of water, I'm going to divide it up into glasses or something like this, right? It's all still there. I have to account for it. And ultimately, the water is the water, just like energy is energy. It's just being held or stored in different ways. One of them, you could store it as height above Earth. Another way you can store it is in being in motion. And these two ultimately are just energies, and one can become the other. So this transfer between each other story here is an outcome. It's not the exact law of conservation of energy, but it is an outcome of the law of energy conservation. Okay, which incidentally says that we don't suddenly have energy appear out of nowhere. We don't have energy suddenly disappearing into nowhere. It's all still there. Okay, just like I'm pouring water into the glasses, if I spill some, it didn't go into a glass, it's there, but I can count that droplet right there is part of the water that I spilled, and I can account for that. And that's the same thing with energy. It may have gone somewhere you weren't expecting, but as soon as you find it, you know how much there has to be in order to make the balance sheet work. It's like an accounting system, essentially. So for this law, we just basically say that energy cannot be made and or made to disappear. Ooh, all right. So in other words, it can't just suddenly appear out of nowhere, can't disappear into nothingness. It's going to be there somewhere. And this is a great concrete factoid to hold on to. This is a good nugget. And this is probably why this law has taken taken over, is used so much in all of the sciences because it's so far always been true. Okay. So I want to go back over here, and I wanted to talk about the names that we have. Motion would typically be referred to as kinetic energy. The energy of motion is kinetic energy. And hopefully that makes reasonable sense, that kinetic is the motion of something. The height above Earth is rather badly named, and it sounds like it could be an energy at some point, but is not yet. And that is not what is intended by this word. In case you are thinking something along those lines, this is known as potential energy, which makes it sound like it's not energy, but it could be at some point, and that is not true, or that's not the intent of the word potential. My guess is that potential, it has potential to become motion energy or kinetic energy. I think that's what the word potential is more geared towards. I don't know for sure, but I do know that I think the word potential energy is rather misleading. And if you maybe go into it thinking it has the potential to become energy of motion and then go do its damage, maybe that would be a better way to think about it. But for us, the energy is there. Potential energy is not something that's not an energy. Potential energy is energy. I guess that's what I'm trying to say, but the words just get all mungled up. It's just amazing. So, so that is the situation with the wording. I will go a little bit further into this, and I'll say that essentially all energies are one of these two types. Either something is moving, and we'll go into a little bit more on that, but that something could be, a car, or it could be an atom. If it's moving, it has motional energy. And it's just that, hey, is it moving? Yeah, okay, well, it's got kinetic energy then. So either the energy is kinetic, or it's to do with a height or a position somehow, or a relative position, or where something is with respect to something else. And that's the potential energy part of it. So either an energy is motional in nature, or it's positional in nature. And those are really the only two buckets that we have for energy. How they get from one bucket to another, well, that's a whole story. Also, we can go through some of the ways to do that. But ultimately, all types of energy fall into one of those two buckets. Okay. Now, if we think about kinetic energy, I said, well, sure, you could have kinetic energy as a macroscopic object. You are running. You have kinetic energy. Your car or your bicycle are moving. You have kinetic energy. It could also be a microscopic object. And by microscopic, I don't mean something that is literally viewable under a microscope. I mean something that actually we cannot see under a microscope, in addition to everything in between the thing that we can't see and the things that we can see. So things like cells, proteins, bacteria, viruses, they all wiggle around and move. They all will at some point have kinetic energy. So do the things that make them up, such as the little bits of the cell there, and the cell walls are made out of atoms and molecules. Those things also have very small, right? They're atoms. They're not going to have huge motion or anything. But they do move, and when something moves, it has kinetic energy, and therefore we say that atoms have kinetic energy. And when atoms have kinetic energy, because atoms, by the way, are in perpetual motion, they don't ever stop. You can't stop an atom. And that's one of those statements that you're just like, really? Why? I mean, look, there you go. My hand is not moving. Well, sure, the macroscopic hand is not moving, but inside, if you look at your atoms that make up your hand, they do jiggle around quite a bit. So atoms have, if you don't mind, KE, kinetic energy. Atoms have kinetic energy, and when they have kinetic energy, we say that something has a temperature. We'll go into this a little bit more in detail next week, or perhaps maybe even as soon as Thursday. But suffice it to say that the thing that we call temperature is the result of atoms jiggling around in perpetual motion and slamming into each other, bouncing off, hitting others, bouncing up, in random perpetual motion. The more vigorous this motion is, the hotter the temperature is, and Vice versa is true. If it's very slow motion, not much kinetic energy, we would say the temperature is low. Now, that that set of little factoids that I just told you took people around 5,000 years to figure that out. It's astounding. Amazing thing that we have actually this knowledge, and that it seems to be usable. The knowledge is usable. In other words, we can say, okay, and we do have the ability nowadays to make several atoms become very, very cold, through techniques thought of with this type of fact in mind. Oh, the atom has kinetic energy. All I got to do is take that away. Okay, how do I do that? XYZ, let's try it. Yes, it works. What do you know? The atoms are now colder, and this thing's very, very chilly. We'll talk a little bit more about this in next week, but this is by no means a straightforward thing to know. So I'm happy to share this with you because I think this right here is one of the most amazing fundamental physics facts that there is. Just when an atom has kinetic energy, it's jiggling around, and that's what we call temperature. So that's a little bit of spiel on kinetic energy. I do want to clarify at this point, since I'm talking about temperature, I do want to clarify the difference between temperature and heat. Okay, so temperature versus heat. Very similar things if used in a popular sense, in a non-physics sense. Often thought of as interchangeable. Not true in a physics sense. In a strict physics sense, these are different things. And they are different because, as I've just described, the temperature is a result of kinetic energy. So this is energy. Actually, I'm just going to do my little abbreviation again. This is kinetic energy. This is water in the bucket, and the bucket's labeled kinetic energy, and that's how we know. Now, the heat here, what's that? This is actually a transfer of energy. This is energy going from one place to another, and it's not energy that is in the bucket. This is energy that is being poured out of the bucket to go to a different bucket. That bucket is also a temperature bucket, so it's kind of funny, but one of the buckets is slightly fuller than another one, so we got to pour it out. In other words, heat transfers because something is hot and something is cool, and the heat goes from hot to cold spontaneously. It will do that. So the heat is a transfer of this. Maybe you could think of it as excess energy in the hotter thing to the lack of energy or the deficit of energy in the cooler thing. I don't want to go into why this happens right now, because like I said, we're going to talk a little bit more about temperature and heat and that kind of thing, maybe Thursday or maybe next week. However, I do want to make that distinction clear that temperature and heat, they are different things. Okay, then I'm going to go back up here to potential energy and this idea that they can transfer between each other. I want to take this idea right here, and I want to look at it. Let's see. I'm going to go all the way down here. I want to look at it down here. And this is, just to go back up here, this is the idea that potential energy, okay? This potential energy, in other words, the height above Earth, it can drop, and then as it drops, it speeds up, and that means that the kinetic energy, right, is increasing. The potential energy, which is the height above Earth, is decreasing, but the sum total of the two is remaining the same. Okay. Now, once you could look at it backwards as well. Take something, throw it in the air. As it goes up, it exchanges its kinetic energy. It slows down, right? This is our visual measurement of kinetic energy getting smaller, is that it's slowing down. The object is increasing in its height as the object slows down. So I throw a ball straight upwards, you will find that it slows down, reaches a peak height, turns around, comes back down, transfers its energy from height back into motion, and thus they can transfer between one another. You'd find on a bounce too, if the ball bounced on the floor and went back up, you'd find the same type of thing. So I want to go back to this transfer between each other. So this is potential to kinetic. All energies can do this. Excuse me. All energies in principle could transfer to become other types of energies, right? Other buckets of energy. In the potential region, we have lots of different types. Because if you think about what I said before, which was that energy is a kinetic type or a potential type. Well, if it's not a kinetic type and it's a potential type, think about how much that encompasses. How much is potential? A lot of stuff is potential energy. So things like not just height above the ground, but also things like chemical energy. Okay, we people use chemicals and how chemicals change and react and dissociate and rebond and give off energy and take in energy. We use that to sustain ourselves, right? We have chemical processes in our muscles, like we take, I can't quite remember, but I think we take something like ADP to ATP, and that chemical change releases energy into our muscles, and our muscles, yeah, let's go get them, you know. And food that we eat also contains chemical energy. These are totally valid energy types. It's a stored energy, and it's in the bonding of the chemicals, and it's known as potential energy. Nuclear is also a type of energy. There is energy in the nucleus. Mostly you might know that because of the stuff that can explode from a nuclear style bomb. All right. We have that. We have elastic energy, things that deform but don't break. They spring back to their original states, much like a spring or a slinky or something like that, or anything really. If you think about it, everything has some level of springiness to it. A tire rolling down the road momentarily flattens out as it contacts the ground. The ground momentarily curves a little bit under its weight, under the tire's weight, and then as the tire rolls on, it springs back to its original shape, and you roll off that particular patch, and the ground goes, oh, I don't need to support that weight anymore. It goes ding. I was in fact driving around today. Was it today? I think it was today. I mean, time. And I saw one of those dump trucks. Now you'll find the dump trucks have this kind of, they have their big sets of wheels, and then they have this one little wheel in the middle. I was supposed to be talking about transfer of energy, but I'm digressing here for a minute. The dump truck. I'm just gonna, right? Well, dump truck here. Yep, got the big cab at the dump truck here. Usually they have something coming out up here. There's a wheel here, and then there's usually a couple of sets of wheels in the back, and then they have this one small little wheel. I always kind of wondered what's that for. Well, it's to it can come down, right? It come down, and then it supports the weight of the truck when the truck is fully loaded. Because what does the truck do when it's fully loaded? Like that, right? And the middle of the truck actually sags under the weight of the tonnage that they put in the bed, so that having that little extra wheel there can support that. It can support the middle of the truck a little bit better. So I saw a dump truck with the middle wheel down today. Anyway, so there's that. This is this is not part of what I wanted to talk about, so I'm going to erase the dump truck. Good and instructive though it was. I want to talk about hybrid cars. This is a great implementation. Hybrid, well, cars, vehicles. Yeah, it's vehicles. This is a great implementation of the idea of energy just being transferred. So what I'll do here is I'll try and describe what a hybrid system technically looks like, and then I'll try and describe a couple of the variations that are being manufactured these days. So a hybrid vehicle, these started coming out in 2002, 2003. It was the first hybrid cars of our modern era. I want to make this clear. These cars have existed. This idea is not new. This idea has existed for 80 years. About that. 70 years, 80 years. Hybrid cars have been built in the past. We've just come back to them. Okay, maybe is a way to think about it. So a hybrid car or vehicle, the powertrain takes the form of hybrid. We use it to mean electric with gasoline. Okay, you could have different types of things like diesel with gasoline. Well, diesel with electric or whatever. Okay, but in this case, I'm talking about fuel of some fossil fuel nature type thing, gasoline or diesel, and an electric motor, which work in tandem with one another. All right, so here, for example, is an electric motor. I'm just going to use this box. Now, that's the electric motor. The electric motor needs batteries. So we're going to have some batteries here. Okay, now the batteries feed the motor. And incidentally, vice versa. The motor can feed the batteries. And this is going to be what we're going to talk about as part of the conservation and the transfer of energy. So this thing can go that way and it can go that way. Right? It's a two-way street. All right, now going over here, we've got another. All right, here's your gas engine. Okay, so gas engine, and this has a connection typically with the batteries. Now, this is not a two-way street, as you would imagine. The batteries can't really help do anything with the gas engine, so the gas engine is here to recharge the batteries, essentially. Okay, now, in the modern formulation, the system has been conceived such that the gasoline engine, as I said, recharge is not really the correct word. It's re-energize the battery. The charge is already there. It doesn't go anywhere. It's the energy that goes into the battery. And the reason that happens is because a gasoline engine can be very efficient. One thing you can think of as an efficiency marker for the gas engine is what's your fuel mileage? Okay. What's your miles per gallon, right? How much MPG do you get for a gas engine? Well, that is a marker for the efficiency of the engine. So this is one thing I really like talking about, because efficiency is one of the things that in my mind is a huge important factor right now, is energy efficiency. It has not always been the case. I'm going to go out on a limb and say that possibly some of you were not alive in the 1970s. Possibly others of us were. I don't know who that might be. Nonetheless, the cars manufactured by the United States manufacturers in those days, in the 1970s decade, those cars were, to put it mildly, crazily inefficient. And the reason you could say that, one could say that because the average gas mileage was somewhere probably between 15 and 20 for the entire set of cars that were made at that point in time. They all had V8 engines. They all had 8 cylinders pumping away, right? Cars nowadays have 4 or 6 or 8, but there's fewer. Pretty much all of them back then were 8s. So that just takes more gasoline, right? They also were very, very heavy, because in the 1970s, plastics were still fairly new. Plastics were really kind of started in manufacturing in about the mid 1950s. And so by the 1970s, they had started to work their way into cars, but not in a very meaningful way. There were, vinyl is kind of a plastic thing. So you'd say, okay, well, vinyl seating, vinyl dashboards, right? That was pretty much the sum total of the plastic in the cars. Nowadays, you know, 1/3 of the exterior panels are plastic in a car. So if you get into a fender bender, you can just kind of like pop them back out, and it's fine, right? If it's metal, then you have to pay someone to take the plenishing hammer and bing, 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 right? And tack, weld the thing back. Well, I've got to cut this panel away, put a new one in, right? So the plastic is a big part of cars these days. Being that they were all metal back then made them very heavy. They were very massive. They had huge engines, and they were, 10, 12 feet long and had only 2 doors. Hence the word land yacht, the phrase describing many of the cars that were produced in America at that point in time. Anyway, nowadays, you can buy cars that can get, upwards of 30, 40 miles per gallon. Back then, it was around 15. So the efficiency of the cars has gone up. Okay, now back to my original point. A gasoline engine can be very efficient. However, we as a country are not set up for this. We have stoplights. They force you to stop, or at least slow way down, which means that you give up all your kinetic energy into your brakes. And then what happens? Your brakes cool off. That energy is now lost. And you speed up using energy from your gas tank. Okay. Now, with a hybrid car, there are a couple of things that can happen here. Okay. A gasoline engine can be very efficient if run at constant engine speed. And you can figure out what this engine speed is. And if you run it at that speed, you can be very efficient with the engine. And I mean very efficient. You could get upwards of 70 miles per gallon if you kept the engine at the speed that it is most efficient. But that's not possible driving, right? Because a lot of the time, you're speeding up, you're slowing down, you're speeding up, you're slowing down, you're speeding up, you're slowing down. Constant engine speed is not a thing that happens easily in cities, even on the freeways these days. In the mornings, it's very backed up. You're going to stop, You're going to go. You're going to stop. You're going to go. When you get your best efficiency is when you're on a long highway and you're in very sparse traffic and you can keep the engine at a reasonable speed and go. And then you'll notice, boy, your engine efficiency, your miles per gallon suddenly goes way up. I used to do a commute from the East Bay down to Hayward because I lived up in the East Bay and I worked in Hayward for a year. And I had this grimy little Corolla. And you know what? I could go 40 plus miles per gallon on the freeway. And since that's pretty much the only thing I use the car for, that's what I got out of the car. And I did lots of science investigations while on the freeway in order to make that happen. So anyway, point being here, with a hybrid car, the gasoline engine can run at very efficient speeds and recharge the battery. In a true hybrid, the only function of the gas engine is to charge the battery. Okay. So this can be run at its efficient sorry, I'm going to put peak here, at peak efficiency. And its only job is to recharge the battery. The battery then powers the electric motor. The electric motor then drives the wheels, which I will just put here. Here's your drive wheels, okay? And that makes you go. Now, notice I put a double-headed arrow here. The wheels can take the energy of the car, step on the brakes, turn that energy back into battery energy. That is to say, if you are whipping up towards the stop sign, or even if you're going downhill and you're applying the brakes, you're taking the energy of being up higher to going down lower. And instead of speeding the car up, you're saying, why don't you recharge the battery? And if you have a hybrid car, you'll see this as you go down, as you're going downhill and you're kind of braking, you'll see the battery go do, 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 do. Okay, because they've made the excellent decision to take the energy that you would have thrown away by using the brakes and route it back through the electric motor, which has now become a generator instead of a motor. And this is a situation where the same thing, the same actual physical object becomes something different, right? Instead of supplying motion, it supplies electricity, right? Normally a motor says, give me electricity and I'll give you motion. But if you run them in reverse and you supply the motion, well, they give you the electricity. This is wonderfulness. And it's something we'll talk about when we do our electricity and magnetism section. And that will be in a few weeks. However, point being that the energy of the car can be stored back in the battery, and then you can take that back and reaccelerate the car. So this arrow here is responsible for what is known as the regenerative braking. Regenerative, meaning it's regenerating the energy. Well, it's not regenerate. Well, is it regenerating it? Well, kind of, but it's regenerative, meaning it's taking it and using it again. It's like recycling it, maybe. Regenerative braking. Okay. That energy goes back into the battery, fills the battery, and then can be used again to speed the car back up. All right, so this is what I call a true hybrid. The only function of the gas engine is to put energy into the battery. So ultimately, the car still runs on fossil fuels, okay? Because the battery is energized by the energy from the gas engine, and the gas engine is run by fossil fuels. Now, what does this do? It does not take away our dependence on fossil fuels. It does reduce it because this is now a more efficient vehicle. Reason being, the peak efficiency of a gas engine is probably around 30, maybe 40% if you're, wow, 40%. Nah, I don't know. This 35 is probably about the tops. I'll say 40, but definitely no more than that. So the maximum possible efficiency, 40% efficiency. Okay, and that let me tell you, that's pushing the ceiling, folks. Okay, your regular engine, if you're in a regular gas car and you're just driving around, you are hoping your efficiency is 20. That's going to be pretty good. Okay, that means that for every 1 gallon of gasoline that you use, 1/5 of it was to actually gone into making you move around. The other 80% just gets thrown away as heat. Okay. An electric motor, the efficiency of an electric motor at its lowest is going to be 80%. Okay. Typical efficiencies are 85, 90%. I'll just say 90. Okay. This is the reason that hybrid cars are more efficient. It's not because there's some other energy source that they are using. They're not. They're using gasoline like a regular gas car. Well, now there's another type. There's the plug-in hybrid. I'll get to that in a minute. The point is that the energy is still coming from fossil fuels for the most part. And it's just that the engine has gotten more efficient. And how the energy is transferred has gotten more efficient. Okay. So this is why a hybrid car is a more efficient fossil fuel user. Now, look, I said that a true hybrid does this. Okay, it only uses the gas engine to charge the battery, and then it only uses the electric motor to put energy into the wheels or receive energy from the wheels, and then to put it back in the battery. Toyota has come up with a hybrid in which they allow, we'll do this in rainbow here. Well, I made this double-headed, but it shouldn't be, so I am going to take this off here. Okay, and go back and do this. Okay, that's better. So Toyota has allowed that to happen. And that means if you really mash the gas pedal, well, I mean, it should maybe be called the electric pedal. Anyways, the speed up pedal. If you push the speed up pedal and you really want more, what they've done is they've engineered the software to say, okay, the battery can supply up to this much amount of energy into the tires, right? A certain power level is what that's called. But if you want more than that, I'm gonna draw it from the gas engine. So if you are in a Prius, for example, or a whatever hybrid that Toyota has, and you push the accelerator down, you push the go fast pedal down, you will hear the gas engine come on. You'll initially hear of the whine of the electric motor, and then you hear the gas engine kick on, and you'll feel the car spurt forwards. Okay, so Toyota does that. That takes it away from being a true hybrid, but at the expense of providing a little more giddy up in the acceleration, because this is, I mean, I don't want to put too fine a point on it, but we are a country of accelerating, right? So much of our vehicle commute is about speeding up, right? From rest or from a very slow speed to a very high speed very quickly, right? We didn't invent drag racing for nothing. Okay, we didn't take drag racing to different heights for nothing. We have all these stoplights one after another, and then we race between them, right? We are a drag racing country. So Toyota recognized this and said, okay, you want a little more pep in your step, you use the gas engine. Okay. All right. So there are different varieties to this. That's a Toyota thing. The GM cars have a different way of doing it, which is that The electric motor drives the car. I'm going to erase some stuff here, but I'll put it back. Well, here's what GM does. Chrysler in particular have a hybrid. They erase that right there. They take away that connection. This fooled me for a long time. Like, what? What do you mean? What? This is not a hybrid car. You've removed one of the fundamentals of being a hybrid car. Well, it's a dual power car, is essentially what a GM or a Chrysler or any of those cars are. It's the actually I should maybe take back GM because Chevy the Volt the Volt I think is more like a Toyota. Okay, so I take this back. Chrysler does this. I know Chrysler does this. They have it this way with no gas engine connection to the battery. So the car is effectively an electric vehicle until the battery is drained, and then it becomes a gas vehicle. Or you go down a long hill and you regenerate the battery, and then it becomes an electric vehicle again for a little while. And then the battery runs out and becomes a gas vehicle again. Okay, there's that. Let's see, I can put all that back in, I think. All right, there we go. So that connection between gas engine and battery is fundamental to being a hybrid electric vehicle, a gas electric. All right. The plug-in hybrid, I'm sure you realized exactly what happens there, right? There's your plug-in. You can really critique the energy in the car. Where does it come from? Even with the plug-in hybrid, you're not getting a significant fraction more energy with the plug-in than you were without. Well, maybe you are nowadays. Battery technology, I will say, the storage capacity of batteries has gone up. I mean, probably 100-fold in about the last 20 years or so with the developments of the different styles of batteries. I mean, it's really amazing. And they're doing nothing but getting better. So maybe this is not entirely true. However, even 10 years ago, if you plugged in a hybrid car, you would fill the battery up and then it would get drained and you would be running on fossil fuels. The fraction of energy that you would have had in the car that was not or potentially not fossil fuel based would have been very small. You can trace energies down to where are they coming from if you are interested. How do you get your energy? Well, if you get it from a power plant, for example, the power plant in Moss Landing is fired by methane. Well, methane is a methane is a fossil fuel, and if you get electricity from that plant, then you're getting electricity from fossil fuels. So the car is still a fossil fuel burning machine. If you got it all from solar, well, okay, that's different. Well, that's clean, right? That's, in other words, it's not emitted greenhouse gases to the environment in creating or transferring, I should say, the energy. Don't want to use the word creating with energy. That's not the way to do it. But in taking the sunlight and converting it into electricity for you, that is a non-greenhouse gas producing process if it is a solar cell. Okay. Okay. So oh, the other thing I was going to say, okay, so you'd say, well, why not just put a solar panel on your roof of your car? it just is not going to create enough energy for you. I use the word create again. It's not going to produce enough. It's not going to provide enough energy for you. In other words, from a solar panel on top of your car, you're talking a maximum of like, I mean, it's not going to be more than 2 square meters. And it's about a kilowatt per square meter. So you're talking about like 2 horsepower at the most. And that's crazy. And that's even assuming 100% efficiency. So that it's not, it doesn't, I mean, you can put one of those solar panels on your car to charge your cell phone. That would work. But to power a vehicle, no, that's not going to be possible at the current way we drive vehicles. Now, it certainly is more than possible to drive a 2 horsepower car. I would say that in our society, it's just not polite. Maybe people are going to be very upset at you if you do this. Okay, so a little bit on the hybrid cars there. I will say this about alternative fuels, since we talked about hybrid cars. I also, here in California, about 15, no, almost 20 years ago, it was almost 20 years ago that came the hydrogen initiative. Hydrogen as a fuel. Is hydrogen really a fuel? No, it's not. It's not a source of energy, right? Like gasoline is flammable. And you'd say, well, wait a minute, hydrogen gas is flammable. Yes, if you mix it with oxygen, sure. However, what's gone on here is that's basically the process by which they've made the energy go into the hydrogen in the first place. Gasoline has energy inherent in it. Hydrogen does not. So it's not a fuel in the sense that there is energy in hydrogen. There isn't. No energy in hydrogen. We put it there. The way hydrogen was conceived as a fuel, as a source of something by which you could run a vehicle, was that because hydrogen is so abundant in this world, right? It's bound up in water. There's 2 hydrogens in every water molecule. So what we did was said, well, energy is supplied first to break up the water molecule. It takes energy to do that. It's like taking a spring and then pulling the spring apart so that it no longer functions as a spring. That takes energy from you to do that. You can't just say, oh, right? No, you have to actively rip it apart. So same thing's true here with hydrogen. The energy is supplied to a water molecule to break it apart. Okay, and then what do you have? You have hydrogen and you have oxygen. Well, oxygen, you can just release the oxygen. I mean, I need to breathe it at some point. The hydrogen gas, though, you save that, right? You save that. And then when you want energy to go, right, in your vehicle, you take the hydrogen and let it recombine with oxygen from the air. When you do that, it gives you back the energy, right? That's like taking a stretched spring somebody has already pre-stretched a spring and they hand it to you and you say, oh, great, thanks. And on one side you put a ball and then you let it go and the ball goes, right? And you get energy from this. So essentially, hydrogen is not a fuel. It's a way of storing energy that we put there that we can get back out later. This is different from gasoline because the uh, the the fossil fuel already had the energy in it, and it's energy stored from the sun because the fossils. What are fossils? Well, they're just dead skeletons, and they're the remains of animals that have died hundreds of millions of years ago, and they've decomposed, and all the stuff they ate and became and grew into is all saved up in their bones. Remember, the energy doesn't go anywhere. Well, what gave them all that? Well, the sun did, because the sun makes the plants grow. Okay, well, a fossil fuel is basically sunlight energy, and it's stored and it's disappearing pretty quickly. So uh, we don't have the ability to store sunlight that easily. Well, I mean, we do now, but we didn't. So uh, you could distill this fossil fuel down into gasoline and you could use that energy and it would make you go. And it didn't seem to be at all harmful. Well, we know, excuse me, we know it differently a little bit now. All right, so I'm going to finish this off. Energy supplied to a water molecule, it breaks it apart. And it becomes hydrogen gas plus oxygen gas. Okay. You save the hydrogen gas and you can what's called recombine. You can recombine it with oxygen, and then that recombination will release energy, and that's where the energy comes from. It was never in the hydrogen. The hydrogen is only a carrier of energy. Hydrogen is this new energy source. No, it isn't. The energy came from when you went in and ripped the molecule apart and then put the hydrogen on one side for someone else to use. And then when they use it, they let it recombine with the oxygen. They get the energy back. And that's how hydrogen fuel cell cars and buses run. I have seen these on buses. I've seen them on some experimental cars. Nobody has really jumped on board the hydrogen vehicle making market yet. Mostly in large vehicles. I have seen it in buses and large trucks. That's a great way, because then the issue is the storage of the hydrogen gas, right? You see this thing here where it says hydrogen gas. So what has to happen is you break apart the water molecule, you give me the hydrogen, it's a gas, I have to store it. Typically, I have to store it in a compressed form, which means I have to go around, I have to drive around with a tank of compressed gas in my vehicle. A tank of compressed gas at high pressures is basically a bomb waiting to explode. So there have been many problems trying to overcome this. Okay. That's why the large vehicle thing makes sense, because a bus, when it gets hit by another car or by a car, it doesn't tend to do bad things. It doesn't tend to like roll or suffer great huge amounts of damage. It just kind of bump and that's it. So the hydrogen would stay safe in its compressed state. Plus, you can store it on the roof. Nobody notices. Buses are so tall. Can't really do that in a car. There's really no place you can put it in a car that someone's going to feel okay about it. So anyway, all right. So there's that on hydrogen gas and hydrogen. Okay. Now, I talked a little bit about this last time. I do want to go into units of the energy, and I can see we're probably about 15 minutes left. So I'll do a little bit on energy units. I'll compare them with power units, and then we'll move quickly into power. We'll probably be done after that. So when you go down here, we'll talk about units of energy. There is the joule. This is the science one, named after Mr. Joule. And then I informed you there was the calorie. There also is the calorie. Oh, that's the same thing as the kilocalorie. I should have written this the other way. Too late now. Right, in the same way that a kilogram is 1,000 grams or a kilometer is 1,000 meters, the kilocalorie is 1,000 calories. And so this is exactly what you think it is. One of these things has a capital C to it. This doesn't. So this thing here with the capital C is 1,000 calories of the second row here, that type of calorie. Okay, what are all these things? Well, it's basically an amount of energy needed to heat water by a certain degree amount, typically by 1 degree in a certain temperature range. So how much energy does that take? Well, it takes a calorie to heat a milliliter of water by a degree. And it takes 4 joules, a little over 4 joules of energy to heat that same amount. Okay. So did I get that right? 4 joules. There's 4 joules in a calorie. Yeah, that's right. There's 4 joules in a calorie. Therefore, there's 4,000 joules in a capital calorie, or kilojoules. There's 4 kilojoules. I could use kilojoules too. Well, that's pretty good. Actually, you do see that on some European food labels, or European non-United States based food labels. Travel to Canada. Yeah, you'll see them right there. Kilojoules on the food labels. Um, Tells you how much you're eating. And then you look at it and go, huh? And you have no idea what's going on. Well, you ate 982 kilojoules. Well, is that good? Or is that bad? 900. I mean, how much is that? I'm supposed to have 2,000. I thought. No. Um, the capital one here, the one that I've been talking about here, this is a food calorie. Okay, this is the one that you eat approximately 2,000 of these a day. Right? That's capitalized. Okay, that's the food calorie. The reason they came up with this unit, and I do not kid, is because if you think about how many calories, little calories, is 2,000, right? If there's 2,000 capital food calories, how many little calories are there? Well, there's 1,000 in each one, so this is equal to 2,000 little calories per day. And people started freaking out. It's like, well, man, I'm going to eat 2 million calories a day. That can't be good for me. I'm going to die. How am I going to eat that much? I'm going to have that much and I'm going to explode into a big ball of calorie bahooey. So they just renamed them. This happens. So that's how the food calorie unit got born. All right, so there's something like a calorie is approximately equal to 4 joules, and therefore one food calorie is about 4,000 joules. So you're eating if you're eating 2,000, I mean you're eating thousands of kilojoules per day. Okay. All right. So those are the energy units, and I showed you this chart once before. Maybe I can show it again. Do I have it here anywhere? Let me see here if we can. Good. Hopefully this is showing. I showed you this. So calories, you can see I have the capital calories, um, uppercase calories on the left column, joules in the middle column, and then compared to TNT. And you can see that TNT, if you go down about a third of the way, TNT has about 1 calorie per gram of energy in it. And what I was telling you on Thursday last week is that things like chocolate chip cookies, uh, butter, where are we here? Chocolate chip cookies have 5 times TNT energy per gram. Butter is 9, gasoline is 11, natural gas is 13, hydrogen is 34, but that's only because hydrogen is so light. It's element number 1. It's very, very not massive. It's not a weighty thing. So most of that is because there's the same amount of energy, but it just takes less of the stuff. So the per gram actually puts on about a factor of 3 there. We talked about that Toyota meteor asteroid last time, and then a couple of nuclear fission and some annihilation things. So butter and gasoline and chocolate chip cookies, more energy per gram than TNT. I think that's very surprising, as I think I mentioned in the class last time. So anyway, you think, oh, calories, little c, big calorie, big C. Oh, who cares? If you cook food, you care, because if you use the one capital T measurement, that's different than the one lowercase t measurement. One's a tablespoon and one's a teaspoon. You want to be careful. One's 3 times the other one. So in this case, it's 1,000, but the idea still remains. That's a deal, and we need to be aware of stuff like that. Let's go back to this. All right, so we're going back to here. Power has the unit of typically watts, named after Mr. Watt. And a watt is a rate. Remember that power is a rate of energy transfer. How quickly did the energy come across? How much of the energy came across? It's a rate. All right. Power is a rate of energy transfer. And therefore, a watt is actually is 1 joule transferred in 1 second. Okay, so you can look at the wattage of your light bulbs, for example, and you can say, well, this is a 30-watt light bulb. Well, there's 30 joules per second coming out of this thing. Not all of them are visible because some of it's infrared and heatish, right? And you can make a comparison between the efficiencies of light bulbs based on their wattages. Okay, because the wattage of a light bulb is how much electricity does it need to put out light. How efficiently does it transfer electricity energy into light energy? Okay. Light, incidentally, is like heat, another way to transfer energy from one place to another. Light is energy that is moving. It is not energy that something has. Right? You'd say, well, light has the energy. Yeah, well, okay, but light's moving, so it's a transfer. Light is also a transfer of energy. Um, so if you take the Physics 10 lab class, then you'll have a chance to play around with some of these things like different light bulbs with different wattages and similar light outputs. Okay. Now, what about other units of power? Okay, well, certainly the horsepower is a unit of power. And somehow this is how we still classify our cars and trucks and things like that in this country is with the horsepower, right? The horsepower. So 1 horsepower is literally gotten from the amount of power that a horse could transfer during an entire day of working. So it would be transferring it at a particular rate the entire day, and you would work the horse at that rate, and it would last 9, 12 hours, right? Whatever your day length is. And you'd say, ah, good, I got a horse that's working at a horsepower for the whole day. All right. So a horsepower, it has some units to it. I'm not going to go into it. Mostly because mostly because I think they're meaningless, and also because I don't quite remember. What is it? Got to be a foot-pound per second square per second or something like that. There's no point in talking about it. But a horsepower is approximately 1,000 watts. If you want to be more technical about it, it's like 750. But you can just round it up and say, for reasonable remembering, it's about 1,000 watts, and 1,000 watts is known as 1 kilowatt. Just like it's a kilometer and a kilogram, it's a kilowatt. Okay, so hence the statement I said prior, which was if you put a solar panel on top of your car. Okay, here's a solar panel. Okay, and this is mounted on top of your car here. Okay, then it probably isn't going to be too much more than 2 square meters. Right, your car isn't too much more than 3 or 4 feet across, and it's probably not got a large enough roof that it's going to be more than 7-ish feet of roof panel space. So a solar panel that's 2 square meters, right? Right? Sunlight's coming down to hit this thing, right? There's the sunlight. Okay, so how much energy is this thing getting? Well, it's getting energy, but it's getting it at a rate, right? How much is it getting per second? Okay, so the sun, the solar energy at our distance from the sun, and certainly this number varies and is not exactly accurate, but it's a good rule of thumb. It's about a kilowatt per square meter, about 1,000 watts per square meter. So you can see this thing would give you about 2,000 watts. That's only 2 horsepower. Okay, that's what I was talking about before. And that's assuming that every single piece of sunlight that this thing captured got turned into into moving energy for your car, into kinetic energy, right? Which is not going to happen. Solar panels, the really good ones, are only about 40% efficient right now. Um, and that's pretty good. So, right, I mean, you're looking at far less than 2000 watts when you look at what the effective power output of this solar panel is going to be. Um, so the sun transfers about a kilowatt per square meter. Um, if you're going to put some on your home, you'll count up some of these square meter panels, solar panels. You're going to look at, most people probably have in the realm of about 10 to 20 square meters worth of solar panel on their house. That's typical. I think during the day in the United States, it's approximately 30 kilowatts. Uh, Maybe that's peak usage, but that's kind of an average, right? That's kind of an average. Um, so anyways, from this statistics, you can see it's not feasible to really power vehicles the way we are used to driving them with solar power alone. However, that has not stopped many people. There is an entire race across the continent of Australia using only solar powered cars. It's a pretty interesting race. I think, actually, I don't remember the name of the competition. But I did follow it for some years. Pretty good fun. The amount of engineering that people can come up with to make cars go on such small amounts of power is really fantastic, and it's really nice to see some people thinking these days. Um, so that was one thing I was going to say, and what was the other thing I was going to say? Oh, the amount of power in California. How much might you need? What if you decided to say, all right, let's power the entire state of California with solar energy alone? What kind of area are we talking about here? Well, you can go look this up. You can look up the land area of California. You can look up what the energy consumption of California is per day, on an average. And you can figure out how much area you will need, or what percentage of the area of California you would need to devote to solar panels to make this happen. I encourage you to go look at the numbers. I don't have them off the top of my head, but I will tell you this is a totally feasible thing to do, uh, from the perspective of how much area it takes. Absolutely no problem should happen, or should be easily happening. I'll tell you what, I'll go look the numbers up. Every now and again you run into people say, well, you'd have to plaster the whole state with solar cells. No, you really wouldn't. You really wouldn't. I'll go look up the numbers and see if I can get back to you on what the exact numbers look like. But in the meantime, I think we'll call that good for today. And I will hope that you had a reasonably relaxing and possibly regenerating weekend. And now we are back to it. I apologize for the lateness of this video, and I will see you Thursday, and we will go on from there. I did post the homework again, just as a reminder. If you've made it this far in the video, thank you very much for watching. I hope that it has been fun and entertaining, and hopefully there has been some knowledge that you have gotten from it. In the meantime, I will see you Thursday. Have a great rest of your, day and a half that's left. Ciao for now, folks.